Welcome to this sixth video lesson on work, energy and power, and in this lesson, the last of this series, I am going to discuss the concept of power, and we are going to look at some very simple calculations on grade 8 level on power, and that should lay a good foundation for you when you work with the concept of power, for instance in circuit electricity in grade 9, grade 10 and grade 11, and then one comes back to power in the latter part of FET in grade 11 and grade 12 when we do work, energy and power again. So let's start off with the concept of power. So the formal definition of power that we are going to work with is that power is the rate at which work is done. Now, let's take you back to the concept of work. So work is basically the transfer of energy. So if we have an object and a force is applied to that object, and that object is moved by that force over a distance d, well, then work is done by the force which comes from the agent. So let's assume the agent was my hand or my arms. I'm not a very good artist, so I do apologize for this. So let's assume that this stick man is me, and the force is being applied by me. So I would be the agent, and the object, this block, would be the object. So force is transferred from the agent, energy is transferred from the agent to the object by means of the force. Now, we've discussed this before. If the object doesn't move, even though a force is being applied, then according to this definition, work isn't done. Work is only done when energy is transferred by a force and causes the object to move in the direction of the force. So, but now let's assume this is the case. Then what happens is the work done by the agent, so we can say the work done by the force, is going to cause a change in the energy of the object. So energy is transferred from the agent to the object. So if I were to now push a heavy box over a distance of, let's say, 20 meters, sometimes you see people in the gym, they're pushing this pile of weights, and there's a structure, and then they push. But by the time they've finished pushing it over, let's say, 15 meters, they are tired because energy has been transferred from their muscles to the object, which is the pile of weights on that structure, increasing the kinetic energy of that structure. So when we look at power is the work done. We can also rewrite this as the energy transferred per unit time. So we could also write this as change in energy of object over time. Not that we are going to focus much on that in this video, because this video is designed for grade 8s, maybe from another school, grade 9. So I just wanted you to be aware of that. We then have a formula triangle that power is work done over time. So we know that work is measured in joules, time in seconds. But now, what is the unit for power? Well, the unit for power is actually something that's quite common. When you go to the hardware store and you buy globes, you would look at in the past, we would buy 60 watt or 100 watt globes, but now that we have more energy efficient globes using LED technology, you'll see, for instance, you're buying a 5 watt LED globe. Now, what does that watt mean? Well, the watt is the unit of power, and the watt is joules per second. So if we look at power, it's work or energy over time. The unit for energy is joules. So if we say, well, 1 watt is the power, and is going to be 1 joule in 1 second. So we can say this is 1 joule per second. So the watt is actually a small unit. 1 watt is not a lot of energy transferred per second. So in practice in the real world, we often work with kilowatts and megawatts. So for instance, our power stations, the average unit of a power station, your coal-fired power station is normally made up of at least 6 units. Each unit has got its own boiler house, it's got its own superheater, it's got its own dynamo, which is driven by the superheated steam. Then on average, those units generate about 650 megawatts. So what that means is every second they are generating 650 million joules of electrical energy per second, which is obviously a lot, but then again, it's driving a grid for a whole country, or it's contributing to it. It's 1 unit of 1 power station. We've got many power stations. We use a lot of energy. All right, so let's take a look at this, and let's look at an example. So we have a boy with a weight of 600 newtons, runs to the first floor of a building in 5 seconds. The first floor is 3 meters above ground. Calculate the power output of the boy. Now, if we look at this, we're making a lot of assumptions here that if the boy is moving upwards, then at a very minimum, the force that is applied by the boy must be equal to his weight. Now, in practice, his weight, it needs to be more than his weight in order for him to accelerate up, but we're going to keep things simple, and we're going to assume that the force that the boy is being moved against gravity is going to be equal to his weight. This boy is going to move, he's going to move like this, but in the direction of the force, he's actually going to move the height difference between where he starts and where he ends. So on the first floor, it says the distance of the first floor is 3 meters above ground. So in the distance of the force, the boy is moving according to the height, which is, in this case, is 3 meters. So if we want to work out the work done is the force times the distance the object moves in the direction of the force. So if we write that down, that's going to be, well, the force is equal to the weight, which is mass times gravity, and the distance is the height. Wait a minute. But this is potential energy. Yes, this is the change in potential energy. You see, when this boy does work to move up against gravity, he's transferring energy from his body to give his body potential energy because he's moving against gravity. So you can see where the formula for potential energy, gravitational potential energy, comes from. So the work done would be this boy's mass. Well, it says this boy actually has a weight of 600 newtons, so we don't even need to work with his weight, with his mass, so it's 600 newtons. So this is going to be 600 newtons times the 3 meters. So the work done by this boy is going to be 1,800 joules, and that is for the boy to walk from the ground level to the first floor. Now, from your own personal experience, you know that you could walk very slowly from the ground level up to the first level, like for instance when you're coming to my science class after break. Or if you're meeting a friend, you could run up those stairs very quickly in a much shorter time. But irrespective, this boy would be doing the same work if he moved from the ground level to the top level. Okay. Later on in FET, we take into consideration what the change in his kinetic energy is, because if he accelerates, his velocity is going to increase, and that also requires work. But we're assuming that this is all done at a constant speed, so there's no change in kinetic energy. So the next question asks is, well, what is the power output of the boy? So power is the work done per unit time. So the power is 1,800 joules. The time, well, in this case, he's doing it in 5 seconds. So this would be 5 seconds. Right, so if we work that out on our calculator, so the power would be 1,800 divided by 5, and that would give us that his power output is 360 watts. Now, what does that mean? Well, that means 360 joules for every 1 second that he runs up those stairs. Now, what if he were to have done the same thing, 1,800 joules of work done, but he were to have done it in 2.5 seconds? So the boy would have had to run up the stairs faster. Well, what is 1,800 divided by 2.5? Well, now we get that the power output of the boy is 720 watts. So more energy is being given off per second, yet he's doing the same amount of work. He's just doing it in half the time. So we can see that going from 360 watts to 720 watts, you're doubling it, but that's because the time is being halved. So there's an inverse proportionality between power and time. So let's now move on to the next example. So in the second example, we have a 5-watt LED light, like one of these. Let's assume it's this one. So we're going to look at one of them, look at that one, and let's say it runs for 3 hours. How much light energy was emitted in those 3 hours? So the first thing we know is that the power of this LED light bulb is 5 watts. So it's always important to understand the concept to the best of your ability. That means every second, that light is going to give off 5 joules of light energy. The time is 3 hours, but now we must be careful, because in our formula triangle, we have, if we can use our formula triangle here, we have that power is work over time. Work is in joules, time is in seconds, and power is in watts. Just whilst we're at it, this W and this W don't mean the same thing. This symbol here is for a quantity, work done. This symbol represents a unit, the watt. So the time is 3 hours, but we need to convert it to seconds. So in 1 hour there are 60 minutes, and in 1 minute there's 60 seconds. So 60 times 60 is 3,600 seconds per minute. So if we work that out, the time is going to be 3 times 3,600. That's going to give us 10,800 seconds. Now, in every one of those seconds, 5 joules of energy is going to be given off. So obviously we need to multiply to get the answer. But let's take a look at our formula triangle. We say we want the work, we have the power, we have the time, so we're going to multiply. So the work done, in other words, the transfer of energy from electrical energy to light energy in the LED, and we know that LEDs don't really get hot, and this is one of the reasons why we use them, is because they're so efficient in transferring electrical energy into light energy. Whereas in the traditional light bulbs, what we call incandescent light bulbs. Those are light bulbs that don't burn in the sense of they don't combust. Incandescent means non-combustible, but they give off light. A lot of the energy, electrical energy, was transferred into heat energy. If you ran a light bulb like that for a few minutes and you put your hand on it, you would get burnt because there was so much heat being dissipated. So, looking here, the work done is the power times the time. So you would normally get a mark for that in a test or exam. So the work done is power, which is 5 watts, times the time, which is 10,800 seconds. And so the work done would be 5 times that, which would give us 54,000 joules, or 54 kilojoules. Remember, there are 1,000 joules in a kilojoule, like there are 1,000 meters in a kilometer. So this work done is the light energy produced. And so our answer is 54 kilojoules. Let's now look at a third example, and this will be the last example we will do in this video lesson. So in example 3, we're considering one of the 650 megawatt units at Kendal Power Station. So if I zoom out, this would be one of the units. This would be one of the units. And this would be a cooling tower here. And this is a stack, a smokestack, where the gases that are produced from the burning of the coal leave the units. So we can see here, you can see that there's energy, there's smoke coming out here. They obviously have systems in place that remove a lot of the pollutants so that not too much pollution, bad gases and products go out into the atmosphere. Once they have used the steam in these units, then that steam, then a lot of it goes out here and they cool it in order to also be able to reuse some of the water. Just to give you an idea of scale, a unit like this, it looks like it might be 1 or 2 or maybe 5 stories high, but that unit there is approximately between 20 and 30 stories high, that building there. So to give you an idea of the scale of these power stations. So let's now take a look here. We have that the power is 650 megawatts, but now we've got to be careful. See, we are not working in the units that we need to work in. We've got to do a conversion. So megawatts means 1,000,000 watts. So we're going to times by 10 to the 6. That is, 10 to the 6 is 1,000,000 watts, which is 1 megawatt. We've got 650 megawatts. The amount of energy that's being produced, the work done, is 1,500 gigajoules. Now, giga is a billion, so that's times 10 to the 9. So these are what we call prefixes. Remember, with prefixes, our prefixes for big numbers, we say kilo is times 10 to the 3, like kilometer. Mega is times 10 to the 6. Giga is times 10 to the 9. And tera is times 10 to the 12. So these prefixes are really very important. We sometimes hear the term terabyte. So terabyte is 1 trillion bytes of information. So let's just take a look. Kilo is times 10 to the 3, it's 1,000. Mega is times 10 to the 6 is 1,000,000. Giga is times 10 to the 9, which is 1,000,000,000. And tera is times 10 to the 12, which is 1 trillion. And they're even talking nowadays about peta, which is times 10 to the 15, which is 1,000 trillion, which I think is a quadrillion. All right, so those are the prefixes that we need to know in physics and in chemistry. So gigajoules is times 10 to the 9. Now we want to know what is the time. How long will it take for one of those units to generate 1,500 gigajoules? So once again, we go to our formula triangle. Power is work over time. Work is in joules, time in seconds, power is in watts, and we want time. So we're going to work with time being the work, electrical energy produced, divided by the power. So there's our formula. Formula we're going to use. Remember, the formula triangle is not the formula. In your first step, you must write down the formula, not the formula triangle. Sometimes learners write down this and think that's the formula, and then they lose the mark because they don't write down the formula that they should extract from this, and then they just do the substitution. So we have that the time will be the work done, which is 1,500 times 10 to the 9 joules, divided by the power. And the power is 650 times 10 to the 6 watts. Right, so if we work that out using our calculators, 1,500 times 10 to the 9 divided by 650 times 10 to the 6, well, then we're going to get that the time it takes is 2,307.69 seconds. Okay, well, that doesn't really make sense to us. How many seconds is that? Well, it's less than 3,600 seconds in an hour, so it's less than an hour. So let's divide by 60 seconds, and that will give us that it is 38.46 minutes. Can you believe that? In only 38.46 minutes, a unit at Kendal Power Station will generate 650, well, sorry, not 650 megawatts, it will do that all the time. 650 megawatts is the amount of joules per second, so it's 650 megajoules per second, but it will take 38.46 minutes to generate 1,500 gigajoules, which is the same as 1.5 terajoules. If we have to divide this by 1,000, then we get terajoules. So if we divide by 1,000, then we get 1.5 times 10 to the 12 joules, which is 1.5 terajoules. So in less than 45 minutes, a unit at Kendal Power Station will generate 1.5 terajoules. Let me just be more explicit about it. Let me write this here in case you're not great with converting units. 1,500 gigajoules. If we divide by 1,000, this is the kind of thing you'll do next year in grade 9, then we're going to get 1.5 terajoules. So what you're doing here is you're making the number smaller, so you've got to make the unit bigger. And you're making the number smaller by 1,000, so you've got to make the unit bigger by a factor of 10 to the 3, which means you're going to from 10 to the 9 to 10 to the 12, which is terajoules. So with that, I end off this video lesson, and this should give you a basic grounding in the fundamental concept of power, how it relates to work and time. That power is the amount of work done per unit time, or the amount of energy transferred per unit time. And we've done basic calculations using the 3 different forms of the power formula. We've worked with power as work over time, we've worked with work as power times time, and we've worked with time as work divided by power. And with that, I end off this video lesson, and I end off this video series on work, energy, and power. I hope it has been beneficial for you in preparing for your exams. Thank you.